Can you all hear me? Good. Well, I'm going to talk to you today about the formation and evolution of protoplanetary disks from a theoretical standpoint. The talk is going to focus really on the different physical processes that drive the evolution of the gaseous component of a protoplanetary disk. So, just to give a brief outline of my talk, I'm going to talk about formation of disks from the collapse of clouds. I'm going to talk about evolutionary processes which are responsible for the exchange and evolution of angular momentum in disks, focusing primarily on self-gravity and the role of magnetic fields. I'm going to talk at the end a little bit about some recent work that's been done on hydrodynamic instabilities, which can also be important for driving disk evolution. And at the end, I will have one slide just describing the final dispersal of protoplanetary disks through photoevaporation. So on to disk formation. So as we all know, if you take a very simple model of star formation, a spherical molecular cloud, which is going to collapse under its own self-gravity, and that cloud is rotating, then we all know that conservation of angular momentum during the collapse will mean that as the cloud collapses initially, if it's rotating rather slowly, as it collapses, it will start to spin up. You will increase the centrifugal force in the equatorial region of the cloud, but collapse will continue to occur along the rotation axis, and that's going to generate for you a structure where you'll have some mass in the center containing a protostar surrounded by a rotationally supported disk-like structure. Okay, so that's a very simple model of star formation. I presume nobody in the room believes that this is the appropriate model of star formation. So let's ask the question, what happens if you have a more realistic model of star formation where perhaps stars are forming in not simple spherical balls of gas where the gas is initially just rotating uniformly, but perhaps in a system such as this, a cloud of gas where internally there are strong turbulent motions, but overall there's no angular momentum contained within the cloud. What happens under these conditions? Well, this is an animation taken from Matthew Bates' website at the University of Exeter. The cloud contains about 50 solar masses of gas, starts off with a turbulent velocity field, so you get a bit of a mess forming. These are the high density regions, which we're going to zoom onto in a minute as we adjust our viewing position. Now we zoom in again, and we're going to see that this region here starts to develop very noticeable rotation. You get a lot of stars forming in these simulations, SP8 simulations. If a dense region forms, which is genes unstable, it gets converted into a particle which represents a star. And here we go. Here's an individual object which is leaving the cloud surrounded by a disk. So what happens in this turbulent structure is that angular momentum originates because you have convergent flows, but where the two convergent flows are slightly off-center from each other, so as they come together, they actually create angular momentum at the point of collision because the convergent flows are slightly off-centered. Okay? So this small component of angular momentum gets converted into essentially a protostellar disk around a point of convergence in the flow. So that's simple gas dynamics without any of the complications of magnetic fields. But we know from observations of the interstellar medium, in particular dense cores, where we examine the magnetic field strength through Zeeman measurements of OH, we know that most molecular clouds associated with star formation are magnetized. From the theoretical point of view, we know that there is a parameter called the mass-to-flux ratio, which, if that parameter, which I've described here as lambda, is less than 1, then the magnetic field prevents the gravitational collapse of the cloud. It will actually hold it up. If that mass-to-flux ratio is bigger than 1, the cloud is able to undergo gravitational collapse in the ideal Mhd limit. Okay? But we also know that if you allow that collapse to occur, and this magnetic so this mass-to-flux ratio lies between a value of about 1 and 10, then there's a transport of angular momentum from the material which is collapsing on the inside and the surrounding envelope in the cloud, which means that the disk which tries to form very quickly loses all of its angular momentum. So you imagine a field line tied to a region of the cloud, which is collapsing on the inside here, that is tied also to material which is further out. As this collapse proceeds, if the object is rotating, material on the inside wants to start rotating quickly, but of course that then twists up the magnetic field, which is attached to some slowly rotating material at the exterior part of the cloud. You have a transfer of angular momentum from the inner regions to the outer regions through what we call torsional alphane waves, and that causes the inner disk to completely lose its angular momentum very, very quickly, and the material just collapses straight into the star. So this is sometimes referred to as the magnetic braking catastrophe. So how to get around this? Well, one might think that adding in some non-ideal MHD effects might help, allowing some diffusion of the field relative to the gas. Turns out that that doesn't really work. The collapse is too quick for the magnetic field to divest itself from the gas. Okay? So let me just go onto this slide here. So this actually shows two examples. One where you have a value for this mass to flux ratio of around about 2 to 4, where you get a very strong magnetic braking and you get a kind of amorphous structure in the center here, but you do not form a rotationally supported disk. Whereas here, if you allow this mass to flux ratio to exceed 10, then indeed you do form a nice disk-like structure. So coming back to what I was saying about how to help this situation, well, you might think, well, okay, well, maybe these clouds aren't so magnetized after all. But if you take the measurements from this particular paper here and convert that into a mass to flux ratio, you get a typical value of about 2, okay? So it's weak enough, the magnetic fields are weak enough to allow collapse, but too strong to allow the formation of a disk. So there's been a lot of work done in this area. Chardy and Hennebel are one group of people who looked at what happens if you misalign the rotation axis between the misalign the rotation axis and the magnetic field, and found that actually that helps a little bit. You can start to form a disk if this mass to flux ratio is greater than around 4, okay? But that doesn't seem to be what happens with the observations. More interestingly, what happens when you have turbulence occurring within your molecular cloud? So what turbulence does, it allows the field to get all twisted up, okay? And certain regions of the cloud are able to then reconnect their magnetic field lines, and that allows the magnetic field to get weakened in certain areas. Furthermore, if you have a turbulent envelope surrounding your collapsing disk, the transport of angular momentum between that turbulent envelope and your collapsing disk is much reduced, it appears. Okay? It's not as easily torqued by the magnetic field. And then also, if you have turbulence, you can generate local misalignment of field in the rotation axis. And these are some images taken from simulations by Seafraid et al. 2012, where the black dots represent protostars which are formed in the simulations, and these yellow features here represent rotationally supported disks. And so you can see in some cases these disks are actually fragmenting. So what I want to show you now is a nice animation which zooms into a simulation undertaken by Åke Nordlund and collaborators in the Starplan Center in Copenhagen. I'm going to show this. I had to convert this movie from a particular format that wouldn't play on my Mac to a new format, so it's going to look a bit ropey at the beginning, but somehow the movie knows that it has to readjust itself partway through. And this animation is of a 40 parsec volume of gas, which is highly turbulent, driven by supernova explosions, and then follow the gravitational collapse of the clouds or local dense regions, including magnetic fields. And what you'll see is the influence that the turbulence has on the formation of individual disks around young stars. So it's a bit green at the moment, but it will snap into the proper color. There you go. Okay, so now we get to zoom in. So it's a static set of images where we zoom in to look at different structures. So looking at a structure now where a dense region has formed, undergoing gravitational collapse on different size scales, 10,000 AU. These are the field lines coming out. The colored material is representing the density of the gas, and we're getting into smaller and smaller scales, 30 AU. So on 30 AU scales, 4 AU, we start to see a surrounding disk-like structure, okay? 29 levels of adaptive mesh refinement, which is quite a lot, I think. And you can see here that you have a nice rotating disk-like structure, but also a magnetic jet, okay, which is pointing out of the region. And here we can see that this is relatively divested of magnetic fields, and so it's been able to form this nice disk. So disks do form. Turbulence seems to help, even in the presence of relatively strong magnetic fields, by divesting some regions of the collapsing cloud from that magnetic, from those magnetic stresses, allowing rotationally supported structures to form. So let's now consider fully formed disks around young stars and ask the question, how do they transport their angular momentum? First of all, why do we need to transport angular momentum? Well, for a number of reasons. Number one, as we heard already from Jenny's talk, circumstellar disks have finite lifetimes, typically between 3 to 10 million years. If you look at different stellar clusters of different ages and count the number of disks which are present, or count the fraction of disks which are present, you find that around young clusters, most of the stars have disks. As you come towards older populations of stars, you find the disk fraction decreases with a typical lifetime of, let's say, around 5 million years. So you need to get rid of the disk. Okay? It doesn't live there forever. Also, if we look not at the infrared part of the spectrum, where you get infrared excess from the presence of the dust in a disk, reprocessing the starlight, but also look in the shortward part of the spectrum, in the ultraviolet part, then you get an ultraviolet excess as well. Okay? And this is caused by accretion onto the star, gas actually falling onto the star, and represented by this ultraviolet radiation. So the conversion of gravitational potential energy into heat, then leading to the emission of ultraviolet radiation from the surface of the star. So somehow the star itself, the protostar, is accreting gas. And in order to do that, it needs to lose angular momentum. So here's an equation. The angular momentum per unit mass for a Keplerian disk is g times the mass of the star times the orbital radius, all square rooted. You can see if you want to move mass from larger radii down to smaller radii, so you accrete onto the star, you need to reduce the angular momentum of the gas. And one thing that we know, and has been known for a long time, is that if you want to transport angular momentum within a differentially rotating disk, you can't ask molecular viscosity to do that job for you because it's just too small, and so we need some other mechanisms for transporting angular momentum within protoplanetary disks. Well, there are two different ways in which disk material can lose angular momentum. One is for a fluid element within the disk to give its angular momentum to another fluid element sitting within that disk. Let's call that internal transport of angular momentum. And one idea for how this might happen is that there could be turbulence in the disk which gives rise to a frictional force, which means that the disk material on the inside, which is going around more quickly, exerts stress on material which is sitting just outside of it. Material on the inside loses some angular momentum, moves inwards. The material on the outside gains some angular momentum and moves outwards, and that overall drives an accretion flow through the disk. Okay? And this effect is often parameterized using the alpha model, which says that the viscous stress in the disk is equal to alpha, a parameter of unknown value, times the pressure. You can write a small expression for the turbulent kinematic viscosity, which is given here, where Cs is the sound speed, disk is h is the semi-thickness of the disk, and alpha is this dimensionless parameter which determines or defines the strength of the angular momentum transport within the disk. And here we see that alpha has to have values somewhere between 10 to the minus 3 and 10 to the minus 2 in order to give accretion rates which agree with the observations of young stars, canonical values of around 10 to the minus 8 solar masses per year. We can also have another mode of angular momentum transport, which is we don't internally transport the angular momentum within the disk by one fluid element giving its angular momentum to another fluid element, but we can extract the angular momentum completely from the disk. And the most obvious way to do this is to have a wind which is launched from the disk, a magnetized wind, where there is a strong coupling between the material which is launched in the wind and the material which is in the disk. And effectively what you do is you launch the wind, you give angular momentum to material which is launched in that wind, takes it off to infinity, and the material in the disk loses a corresponding amount of angular momentum and accretes towards the central star. Okay? So this is not internal transport, it's just removal of angular momentum from the disk. So I'll talk about different processes which represent both the internal transport and also the extraction through a wind. First of all, self-gravity. So this is a means by which fluid within the disk will transport its angular momentum internally. what we know is that if a disk is close to obeying this parameter, this Toomre criterion for gravitational instability, namely that the sound speed times the angular velocity divided by g times the surface density of mass in a disk, if the value of Q in a disk is around 1, then we know that the disk is going to be gravitationally active. Now, this criterion is equivalent to saying more or less that the mass of the disk divided by the mass of the star is approximately equal to the aspect ratio in the disk, and we expect this to be around 0.1 or so the disk mass is going to be around 10% of the solar mass in order that this Q value hovers around 1. What we know is that when you have a disk in this state, it's going to excite or self-generate spiral waves, okay, which will be shock waves, and these are able to heat the gas. So if we think about the thermal equilibrium, we also allow the gas to cool through basically irradiation from the surface, okay, and we have a cooling rate. And the nonlinear outcome of this situation depends on how quickly the gas is cooling locally. If we write the cooling time in terms of the orbital angular frequency, okay, then another way of saying this, if the cooling time is about half to 1 orbital period locally in the disk, then the disk is going to be able to fragment into bound clumps. And this is shown by this animation here. You see the spiral waves being generated, and then in certain regions of the disk, we find that these spiral waves break up into these discrete clumps. Okay? This is occurring on size scales of typically 50 to 100 astronomical units, because that's where this cooling time typically has this rather small value. Okay? Now, we also know that if we put a dense clump of gas into a self-gravitating disk and allow it to gravitationally interact with the disk, it will also undergo very rapid inward migration. So here's a bunch of simulations undertaken by Clermont-Baruto et al. They're starting at about 100 astronomical units, and what you can see is that these objects are migrating inwards on timescales of about 5,000 years. The orbital period at 100 AU around a solar-type star is exactly 1,000 years. So this is migrating inwards on a timescale of around 5 local orbits. Okay? So this is one idea for the origin of FU Orionis outbursts. FU Orionis outbursts are young stars, or FU Orionis objects are young stars, which are observed to undergo very strong brightening in their luminosity. FU Ori itself was seen to brighten from around 16th magnitude in 1937 up to about 9th magnitude, and it's remained very bright ever since. And this is interpreted as being an indication that the disk is very rapidly accreting its material onto the central star. So one idea which has been put forward is that the inward migration of these clumps may actually be driving these FU Orionis outbursts in these strongly self-gravitating and rather young protoplanetary disks. Now, the other situation that can arise is that the cooling time is somewhat longer than this canonical value of between 3 and 5 times the angular velocity in the disk. Okay, so somewhat longer than the orbital period. And in this case, we know that the disk is able to maintain a state of what's called Gravita Turbulence, where spiral shock wave heating is balanced by radiative cooling without the disk actually fragmenting. So this is shown here. You can see there are no fragments actually occurring in this particular simulation. So this situation also can give rise to a state where the disk can also undergo outbursts. The idea here is that you have a surrounding cloud of material which is raining its material onto the surface of the disk at large radius. The disk undergoes a period of strong gravitational instability, drives the material inwards, and as that material comes towards the central regions of the star, the disk actually heats up. This is the temperature shown here. This is the surface density after one of these strongly self-gravitating periods of evolution of the disk. Material is driven inwards, heats the inner disk, where the temperature can rise above around 1,000 Kelvin, And when you get 1,000 Kelvin in the inner regions of your disk, you're able to ionize some of the material and cause the magnetic field in the disk to strongly couple to the gas, driving a very strong accretion flow onto the star. So you don't just need clumps of gas in order to migrate inwards. You can also have an FU or ionist outburst by driving temperature upwards, by accreting rapidly through self-gravity, drive the temperature upwards, increase the ionization fraction locally, couple to the magnetic field, and then drive a strong accretion flow onto the star. And this is just some plots showing accretion outburst in a paper by Jehan Bai 2014. And you can see these are accretion spikes which are occurring here. So that's self-gravity. You can either generate clumps, or you can have a steady state Gravita Turbulence operating in the disk, which drives angular momentum transport and also mass flow in towards the central star. So a favored model for how disks can accrete in the presence of magnetic fields is the idea that the disk is unstable to Magneto hydrodynamic turbulence through an instability which is called the Magneto rotation instability. Let me just take a couple of minutes to explain how this works. Imagine that we have a vertical magnetic field line. We're looking at a disk, edge on. Okay. This magnetic field line has two clumps of gas sitting on it, A and B. We're in the ideal MHD limit, so the two clumps of gas are actually bound to the magnetic field line. We move one of the clumps of gas inwards towards the star and the other clump of gas further out. The one on the inside wants to rotate around the star at the local Keplerian angular velocity. So it wants to go faster. Let's call that clump A here. Clump B, which is sitting a little bit further outside, wants to rotate a little bit slower. So as we allow this situation to evolve, the magnetic field line acts like a spring, joining the two clumps of gas together. And so what happens is that because clump B is rotating around the star more slowly than clump A, it pulls back on clump A as clump A tries to orbit around the star. So the magnetic field, as I mentioned, acts as a spring, joining the two objects together. So clump A feels a force pulling back on it, okay, due to clump B. And as clump A feels a force pulling back on it, you remove angular momentum from clump A and it tries to spiral inwards. Similarly, clump A feels a force pulling it forwards along its orbital trajectory. That gives it angular momentum, causes clump B to want to move outwards. And so you have a situation where some small initial perturbation in the system, where you displace clump A and clump B, grows over time because of the way in which the magnetic field is transporting angular momentum between them. And a small initial perturbation will grow exponentially due to this. And so you have an instability. Okay? The growth time is around the orbital period. And this instability, as we'll learn in a few minutes, can be modified or quenched by non-ideal MHD effects. But this is a favored model for how angular momentum transport could, in principle, be occur in a protoplanetary disk. So simulations, I'm going to show another one. This is also a simulation that I had to convert in order to play on the laptop. So it will do a similar thing, but it shows the velocity field in a simulation of a disk which is undergoing fully developed magnetorotational turbulence. Sorry, it will snap into the proper color scheme in a minute. There we go. And now you can see it here. So it's a global simulation undertaken by Mario Floch and collaborators. Here you can see an edge-on slice of the disk, and then here we're looking at the disk surface, and here we're looking towards the midplane. Find the turbulent velocity field is about 1/10 of the sound speed near the midplane. Near the upper regions, it's somewhat higher because the magnetic field is able to move the gas faster there. And then as we look at what's called the plasma beta parameter, this is the strength of the magnetic field relative to the gas. We find that in the upper regions, the disk is dominated by a strong magnetic field, whereas in the inner regions, it's dominated by the gas pressure. Okay? And we get angular momentum transport corresponding to alpha values of between 10 to the minus 3 and 10 to the minus 2 out of these kind of simulations, which is kind of what you need in order to explain the observations in principle. The trouble is that protoplanetary disks do not behave like ideal MHD laboratories. Okay? The reason for that is that the ionization fraction in the disk is very low. Typically around the midplane, values of the electron fraction are 10 to the minus 12 to 10 to the minus 13, a long way away from being in the ideal MHD limit. Okay? So we need to consider non-ideal MHD processes. In particular, These are processes which allow the magnetic field to diffuse through the gas. So in the ideal limit, of course, we know that the magnetic field and the gas experience flux freezing, and so whatever the gas does, it drags the magnetic field with it. Now we're in a regime where this no longer happens. So there are three different processes that need to be considered, which operate in different parts of a protoplanetary disk. The first one occurs in sort of cool, dense regions of the disk where the ionization fraction is very low. It's called ohmic resistivity. In ideal MHD, both the electrons and the ions are tied to the magnetic field lines and gyrate around them. Okay? And wherever they move, they take the field with it. But in the operation of ohmic resistivity, what happens is the electrons and the ions collide with neutral species in the gas that get knocked off the field lines. Okay? So that provides a resistivity in the fluid. In ambipolar diffusion, you tend to be looking at low density regions where the magnetic field has ions, electrons tied to it, okay? But the collision between the ionized species, the collision rate between the ionized species and the neutral species is extremely low, so the magnetic field can move around and do its own thing, and the neutral component doesn't really feel that very strongly. So there's a decoupling between the magnetized component and the neutral component in the flow. And then the Hall effect is an intermediate regime where only the electrons are attached to the magnetic field lines and the ions are not. Okay? And you can write the induction equation, and for each of these different physical processes, there is a term which modifies the way in which the magnetic field evolves. Now, if we consider a protoplanetary disk, we can ask the question, whereabouts in the disk do these different processes operate? If we look in the very inner regions, okay, at around 0.1 AU or so, this line here, this is basically temperature versus density here. This line draws a line through a protoplanetary disk midplane, starting at 0.1 AU all the way out to 100 AU. In a typical disk model, we find in the inner regions the ohmic and the Hall terms dominate, and in the outer regions the Hall and the ambipolar diffusion terms dominate. This shows a similar trajectory through a disk, but in the upper regions where we find it's usually the Hall term and the ambipolar diffusion terms which are dominating. Okay? So what do these do to the evolution of the disk? Let's consider ohmic resistivity only for the time being. Okay? So the disk here, okay, is expected to be thermally ionized in the inner regions around the inner few tenths of an AU. So this means that here we could sustain fully developed magnetorotational turbulence here. Okay? Once the density gets above about 1,000 Kelvin, we can ionize potassium, and that provides enough free electrons to give good coupling to the magnetic field. But between about 0.3 and 20 AU, if you only consider the influence of ohmic resistivity, what you're going to have is a cold, dense midplane region, okay, which is effectively magnetically dead, and then only the surface regions can be ionized by X-rays and cosmic rays in order that you can generate MRI turbulence there. So this is what we call a classical dead zone type structure. Turbulence at the top, and then a relatively quiescent region around the middle. Okay? So you can accrete material through the top, but the interior region remains relatively inert. This just shows what happens to the magnetic stress in the dead zone. The dark curve here shows a case where you have fully developed MRI turbulence. This is the equivalent alpha value in the simulation. You get a value here about 10 to the minus 2. But you have a dead zone model. Let's take D2 here. What you can see is the magnetic stress in the midplane region gets very, very small, down to 10 to the minus 6 or so. Okay? What happens if we add ambipolar diffusion? Well, you end up with, if you do that in the case where there's no net magnetic field in the disk, so let's imagine we have a disk where the magnetic field doesn't have a component which goes all the way through the disk, so that you effectively, the magnetic field would need to be maintained internally through a dynamo. What we find in that case is that the alpha values which you get throughout the disk are absolutely tiny, 10 to the minus 7 or 10 to the minus 6. So ambipolar diffusion completely quenches the turbulence in the upper regions of the disk. Okay, so you get rid of the active zone and you just end up with a dead disk. Okay? Now, if you consider a net magnetic field, then the situation changes enormously. We return to a picture which is a traditional one for the launching of winds from disks, which is the idea that if you've got a vertical field, then this field can lead to the launching of a jet through, or a wind, through a magnetocentrifugal wind. Okay? It's a traditional wind picture where what you require is a strong vertical magnetic field, but then also an angle of inclination between the magnetic field and the normal to the disk of about 30 degrees. And when you have that, you can actually launch a wind. Basically, the rotation of the disk takes material and slings it out of the system. So this shows some simulations of this process actually operating. We have ohmic resistivity and ambipolar diffusion operating in the disk here. The white lines show the magnetic field, and the arrows show the launching of the wind from the surface of the disk. Okay? So this is a global simulation where we actually see this happening. And what we find is that this magnetic magnetocentrifugal wind can actually lead to accretion rates through the disk, which are at the level of around 10 to the minus 8 solar masses per year. But it should be noted that the details of these calculations, the actual amount of mass lost in the wind and the accretion rates, things like that, do depend a lot at the present time on simulation details such as the height of the computational domain. So this is very recent work, and at the moment I would say it hasn't converged to a situation where we know exactly what the accretion stress is and how much mass is being lost from the wind. Now, if we add the Hall effect into these calculations, something very interesting happens. What has been known for some time and was predicted by Salmeron and Wardle in 2012 is that you can actually possibly reignite the disk in the dead zone if the angular velocity and the magnetic field in the disk both point in the same direction. So you get this very interesting thing where the Hall effect doesn't really do anything if the magnetic field and the angular velocity are anti-parallel, but if they're parallel, you can get quite a strong effect. So this shows the stress in the disk when you have a traditional dead zone with just ohmic resistivity. This is what happens when you add ambipolar diffusion, and then suddenly if you add in the Hall effect as well, you can get a very strong increase in the amount of stress or accretion which is occurring in the midplane. This particular calculation took place with a chemistry which was grain-free, so dust grains are very important in disk chemistry. So what happens if we add in a grain chemistry is we find that this stress in this region is reduced somewhat from a value of around 10 to the minus 2 for the alpha value there, more like down to a value of around 10 to the minus 3. In this plot here, this is the height versus the stress in the disk, and you can see you have a midplane region here where you've reignited it essentially. You're able to drive an accretion flow through the central regions when you include the Hall effect. The interesting thing is it only happens when you have this particular orientation of the field and the angular velocity, and I don't know myself how that in a sense maps onto observations of accretion rates in disks. As far as I know, we don't have two types of disks, those that show strong accretion and those that don't. So I think there is more work to do here to really understand how these models actually map onto the observations. So let me now move on and quickly talk about some hydrodynamic instabilities in the last couple of minutes, which are of relevance to the dynamical evolution of accretion disks. We start off with the Rossby wave instability, which is of interest because there are some indications in observations that this may be operating in disks. So we have a particular quantity, let's call that quantity L, and what we know is that if there is a maximum in this quantity or an extremum in this quantity in some localized region of the disk, it can give rise to the growth of vortices. This is shown here by this plot here where we have three vortices forming where a local pressure bump was put into the disk here, an axisymmetric pressure bump. Okay? So these can be triggered, it's called the Rossby wave instability. It can be triggered, first of all, let's say at the interface between an active and a dead zone, a region where the disk is actively accreting inwards and it comes into contact with a region where the disk is not able to accrete so efficiently. So you build up mass there and you can generate a vortex for that process. Also, if you have a gap being formed in a disk due to the presence of an embedded giant planet, you'll also get a pressure bump at the edges of the gap, and if the viscosity in the disk is low enough, you can also get a vortex there. There's some indication that from ALMA images of Ophiuchus IRS 48, we see that the millimeter dust is concentrated on one side of the star. Okay? And a model that's been put forward to explain this is that indeed we have a planet orbiting around this star, which has created a gap with an interior cavity. At the edge of the gap, you get a pressure bump, which then forms this large single vortex, and that vortex is very efficient at trapping the millimeter dust and giving rise to this feature, which is shown here. So that's just one area where we have a comparison between models and observations, particularly these recent ALMA observations showing these one-sided features in the millimeter emission. So finishing off very quickly, there are a couple of other hydrodynamic instabilities which could be of importance both for driving accretion in the disk and also for planet formation because of their ability to generate vortices. One of them is called the subcritical baroclinic instability, which requires that the entropy gradient in the disk is negative. In other words, in the absence of rotation, the disk wants to be convective in the radial direction. This is an instability which is in some sense what we call a nonlinear instability. That means you need to put down quite strong perturbations to the velocity field in the disk. But if you do that with these conditions satisfied, what you find is that this disk is unstable to the growth of significant number of vortices. It depends very much on the cooling time in the disk, and the cooling times need to be relatively short. So this is another instability which is likely to operate in the outer disk regions. And then finally, with regards to these instabilities, let me talk very quickly about the vertical shear instability. So this is an instability which has been known about for many years in the context of the radiative zones of stars that become, an interest has grown in it recently. This shows basically an edge-on profile of a disk. And the only thing that we do here is you put in a radial temperature profile into this disk model. It turns out if you look at the disks, the equilibrium equations for an accretion disk with this kind of temperature profile, when you have that, it generates a disk which doesn't just have shear in the radial direction due to the Keplerian motion, but also that as you move away from the midplane towards the top of the disk, you also slow down your rotation, okay? And this gives rise to the so-called vertical shear instability. And simulations show that it can generate an alpha value of around 10 to the minus 3, 10 to the minus 4, and also can generate strong vortices in the disk. It also requires a short cooling time, meaning it would only operate in the outer regions of the disk. Finally, let me just say a couple of words about dispersal. The viscous evolution of a protoplanetary disk cannot remove all of the disk material. We need some other process. The reason for that is that when you have a viscously evolving disk, most of the material accretes onto the central star. A small fraction of it expands outwards, absorbing the angular momentum, moving away from the star. So how do we remove the remnants of the protoplanetary disk if that's the mode by which the disk is accreting? The most likely explanation is photoevaporation. And basically what happens is the ultraviolet radiation, both the extreme and the far ultraviolet and the X-rays, heat the surface of the disk. And beyond the radius, where the sound speed in the disk equals the escape velocity from the central star, you're able to launch basically a hydrodynamic wind from the surface of the disk, which can escape to infinity. Okay? Now we know in the Orion Nebula, the O stars are able to very rapidly evaporate the disks with timescales of about 10 to the 5 years. But in the absence of an external O-type star, we have to rely on the central protostar, and their recent models have suggested that both X-rays and FUV photons from the central star dominate the evaporation of an isolated T Tauri disk, and actually are able to generate mass loss rates which are competitive with the accretion rates of the disk on the order of 10 to the minus 8 solar masses per year. Okay, thank you very much. Yes, but also, I mean, you could, sorry, yes. So a question about, I think it's really the origin of the magnetic field in the disk, which is capable of launching the wind, because your statement is that the dipolar field, which is associated with the star, is not able to do that. What you need is open field lines, okay? So in that case, you need to have a magnetic field which is brought in with the collapse of the molecular cloud which formed the disk in the first place. So these are not magnetic field lines which are generated by some dynamo process within the star. They're part of the actual star formation process itself. So you need to bring this field in as the disk is formed and as the material is accreting towards the central star. Okay, so that's the origin of that field. It's got nothing to do with the star itself. Does that help you? Yeah, okay. Yeah, it would depend on the infall rate, because in the second model, yes, okay, so it's a question about FU Orionis outbursts and whether or not the two different models have different timescales associated with them. Well, it depends on what it is that's ultimately driving A, the gravitational fragmentation, or B, just the gravitational activity in the disk, okay, which allows large-scale mass flow to occur. And that's always going to be driven not by the internal processes within the disk, but actually the speed with which the material is actually being supplied to the outer region of the disk. Because what happens is that you go through a phase when the disk is massive, where you either fragment or you have kind of quasi-steady Gravita Turbulence operating, okay? But under with both of those physical processes operating, they very quickly drive material in towards the central region, okay? And so then the outer region of the disk would be relatively low in mass, okay? So you'd have to wait for the mass to grow in the outer regions of the disk in order to drive the next FU Orionis outburst, yeah? And so that's then driven by the infall from the surrounding molecular cloud, okay? So it's not something which is thought to occur repetitively for an isolated disk, but only a disk which is being fed by an external molecular cloud. So it's that feeding of the disk which drives the timescale rather than the internal processes.